Hi, welcome, and now I will move on towards one of the main extensions of Bayesian SEM that is called Approximate Measurement Invariance. So this is a Bayesian take on how we can do measurement invariance analysis that is pretty common in psychometrics and latent variable models, but from a Bayesian point of view. So just a quick recap, the Bayesian SEM it's basically the same idea as a regular SEM, but you need to specify the priors for all of the parameters that you have and whether you need to be informative or not. The fit indices change a little bit, and the parameter estimation is by MCMC. And also you can check for modification indices. Okay, now measurement invariance is also called multi-group SEM and also diff analysis, and assesses the degree of equivalence between groups. So basically it will create one latent model per group of a known variable and then try to estimate them. Then afterwards we will start to constrain families of parameters, for example, and there's a certain framework on that. Configural invariance just assumes that latent structure is equal, and that's it between groups. The metric invariance also forces loadings to be statistically equivalent between groups. Then if we move on towards intercepts, it's called scalar invariance, then strict invariance with hidden residuals, and there are other measurements and other levels, for example, restraining correlation between factors, modification indices, or something like that. Okay, if you want a quick review of multigroup CFA or measurement invariance, here is a table that sums up what is the meaning from and what type of comparison can be applied, because remember that measurement invariance analysis makes some guarantee evidence on comparing the means of groups, for example, or scores between participants of different groups. Okay, now if we want to make it Bayesian, one intuitive answer or one intuitive alternative should be getting the exact same framework. So it would be the classic measurement invariance, but with a Bayesian estimation. This is not very used, but it can be done. You can estimate one model per group, then obtain the fit indices and start restraining the parameters. For example, using the following framework of configural, metric, scalar, and strict invariant levels. Then you could start to compare the fit indices, for example, the AIC, the LUCV, or whatever you want, to then conclude that you can make a Bayesian estimate of the classic measurement invariance analysis. However, there are more interesting things happening here. Right now, in scientific contributions, we can encounter easily with, for example, multi-country samples with many groups or large samples, and normally interested in comparing latent means. Here is an example of what I'm trying to say. This study about well-being had a lot of countries with a sample by each country, and were interested in comparing the latent means in well-being. Okay, so measurement invariance usually does not reach the scalar level because it just needs to be one parameter being significantly different to break the invariance level, and also can be prone to show differences that are really there in the population, or that they are there but they are minor. For example, that between two countries, one of the loadings of the scale is slightly higher or slightly lower. And of course, there are other issues like parametrization or skewness. There are some review of techniques if you want to know more, and also a comparison between them. Okay, so what we can do about that? So from Bayesian perspectives, we can make what is called an approximate measurement invariance analysis. This is basically making a Bayesian inference on the differences between parameters. For example, if we are comparing two groups, the factor loading of the item 1 would be subtracted between group 1 and group 2, and then we will create a prior for these differences to then obtain a posterior of these differences and see if that is suitable. Okay, so now we will not only just specify the priors of all of the parameters of a latent model, but also we need to specify the priors of the differences between parameters across groups. For example, loadings, differences in loadings could have priors of normal distributions with a mean of 0, and a standard deviation of 0.1 or 0.01, because they should be around 0 and be really homogeneous in that. But they would be allowed to have tiny variations. Okay, so after this specification of priors, you can have an MCMC estimation that you need to check that everything is okay. And the output will be the posterior distributions and the fit indices of this analysis. Okay, so something that you can do is that you could start from a non-informative point of view, for example, leaving a lot of room for the differences to take place, for example, a standard deviation of 1, and then start to be restrained, because you can estimate a lot of models and compare them without inflating type 1 errors. Therefore, you can get the presence and allow them of small and negligible differences that wouldn't block you for assuming an approximate invariance between groups. Okay, so the only thing that you need to take into account is to specify these priors, the priors of the differences between parameters, and prioritize the DIC index. Okay, this idea is actually not unique from a Bayesian perspective. There is a frequent development towards this that is called the alignment method. And also you can do multi-level CFA using the group as a level 2 variable, and also mixture models of CFA. Here's an example to see how we can do an approximate measurement invariance. We have a sample of 5,000 individuals from 7 countries, and we have data from an optimism and pessimism scale. These are the items, okay? So here is a descriptive plot for all of our countries, and as you can see here, it is very similar between each other, except for some countries. For example, in Spain, all of the pessimism items are higher than the others, and some items are different in some other countries. Okay, so if we try to make an approximate measurement invariance, we can allow for cross-loadings, and also we can model the differences in cross-loadings. However, this table sums up how we can do that in priors in differences in loadings, and as you can see here, a prior of normal distribution of mean 0 and 1, a standard deviation, this is the most non-informative one, and then 0.5, 0.1, 0.05, 0.01, 0.005, and 0.001. You can see here that DIC starts to increase and then decrease and then increase again. The BIC decreases until this point, and the PPP is always lower than 0.05. So you can, prioritizing the DIC, select this model as one of the approximately invariant model in loadings. Because why? Differences in loadings are modeled with a prior of mean 0 and standard deviation 0.05. And the DIC indicates that this is the best model, except from this, because it has convergence issues, right? Okay, so we could say that it is assumable to have a model with 7 countries that the loadings have an area of effect between very small values around 0, because the standard deviation is so low, okay? Of course, all of these models will produce trace plots, autocorrelation plots, density curves of each chain, and that need to be checked that everything is going all right, okay? This is another thing that we can do, for example, differences in intercepts, and as you can see here, we need to be way more informative than with loadings, because the best model assumes a 0.5 of standard deviation, and maybe it's caused because of the differences in the other countries, okay? So that's a way of how we can do a Bayesian approximate measurement invariance analysis using Bayesian SEM. And as before, this is some documentation and some links that you can have. And there's a really nice chapter on approximate measurement invariance in Leck and colleagues that is also in the presentation. Okay, so this is the end of my presentations on Bayesian psychometrics.